Okay, the next speaker is Peter Troyan from University of Virginia. He's an assistant professor in economics there. Peter is going to speak about their joint work with Marek, Pycia on obvious dominance and random priority. This is the best paper award winner for EC'19. So let's welcome Peter.
All right, thank you very much. Janne, at the end of his talk, mentioned he had some work in strategic complexity, which I was hoping he was going to talk about because that would be able to shorten my talk a little bit. But he did not, so I'll tell you about his work too a little bit as we go along. Some more Janne. I'm going to talk about some joint work with Marek on obvious dominance and random priority. So we're going to look at complexity kind of from a different perspective, more from an economics perspective. And the idea here is that complex mechanisms may be difficult for people to play, obviously, which may undermine some nice theoretical results that we have. And one common standard of simplicity that is often used is so-called strategy proofness, right? But the issue with strategy proofness is that there's evidence that agents may not necessarily always understand when a game is strategy proof. So the canonical example of this is sealed bid versus ending auctions, right? So if you're familiar with Sheng Wuli's paper, that's basically this here, where these are strategically equivalent according to the revelation principle, but people seem to be a lot better at the ascending auction than the sealed bid auction, right? Similarly, and I'm more of a matching type person, we have strategy-proof mechanisms there, like deferred acceptance, where there's evidence that people make mistakes in not just in the lab, but in real, high-stakes decision problems. So that's going to motivate our question of what mechanisms are simple, but different from Janne, we're going to do this more from an economic or a strategic perspective, okay? So just to preview our contributions, so first we're going to introduce a new general class of simplicity concepts that are going to relax the foresight abilities that we require of agents in extensive form games. So we're going to be working a lot with the extensive form, and we'll show, I've already briefly mentioned Sheng Wuli's obvious strategy proofness. This will be an important special case of our more general concept. The reason we're going to do this is because, as we'll see, some obviously strategy-proof mechanisms are indeed quite simple. Others may not be. And to further explore that, we'll further characterize the full class of simple mechanisms in certain canonical social choice environments, both with and without transfers. And then finally, as an application of our ideas, we'll show that in no transfer settings, we can characterize the random priority mechanism as the unique mechanism that is efficient, fair, and simple to play. So if you don't know the name, I'm sure you know the mechanism. We just have a bunch of objects we want to allocate, and we just pick an ordering of everyone in the room. We call you up one at a time. You take your favorite thing. Some people call this random serial dictatorship. It's the same. We're going to call it random priority. This is a widely popular mechanism. And we explain the widely popularity of this by showing that if you care about efficiency, fairness, and simplicity, it's basically all you can do. Okay? So that's what we're going to do. So, all right, what's our environment? The environment is going to be just a general, in the paper, so we have a very general social choice environment. There's just some outcomes, finitely many of them. People have preferences over these outcomes. We can work with models both with and without transfers. To escape from things like the Gilbert-Satterthwaite theorem, we need to impose some restrictions on the preference domains. And a key assumption for many of our results is that the preference domains of each agent are sufficiently rich, okay? So I'm going to refer you to the paper for the formal definition of that. This is a short talk. And for the talk, I'm going to have you just think of this setting of object allocation without transfers and single unit demands. So this kind of object allocation problem where each person wants exactly one object, okay? And at various points, I'll bring back transfers and talk about auctions at various cases when we have results that are of particular interest. But unless otherwise stated, what I want you to have in mind, just object allocation. And the notation here is going to be a set of agents, a set of objects. We have the standard notation for strict preferences. Richness here will correspond to the idea that every strict preference ranking of the objects is possible for each agent. But of course, you're indifferent over outcomes where you get the same object, but other objects are allocated differently. Okay. All right. So let me now remind you what obvious dominance actually is. That's going to be our starting point. So I'm going to just introduce this notation of utility function pretty much only for this slide to make these definitions easier to state. So this is going to be i's utility when he plays S, I, and his opponents play S minus I, and we start at a history H. Okay? So the histories are going to be important. Extensive forms are important. And then Sheng Wu says that SI obviously dominates SI prime if, starting from any earliest history at which they differ, the min over the worst case over SI is better than the best case, at least as good as the best case over SI prime, right? So the idea is we have two strategies. They tell us to do the same thing for a while. At one point, one says go left, the other says go right. Even for left to be obviously dominant, the worst thing that can happen in any continuation game here has to be at least as good as the best thing that can happen over here, right? Then a mechanism will be obviously strategy proof if every type has an obviously dominant strategy. And Shengwu has a lot of nice results that shows that these are robust to agents who may have limited ability to contingently reason by state, or maybe are only given a partial description of the game, okay? That brings us to our first question, which is, so what types of games satisfy this, right? So it's a solution concept. What can we do with it? So there are some nice games that are obviously strategy proof in this no transfer setting. Extensive form serial dictatorships, random priority, they'll be OSP, very easy to show. But is that all, right? First I'm going to show you that that is not all. And here's an example of the types of game, another type of game that is obviously strategy proof. So in this game, agent I starts by being offered A, which is an object. We say that he's offered to clinch object A, right? We call that a clinching action. Or he could pass. If he clinches the object, he takes it and he goes home. If he passes, he's still in the game, and now it's J's turn. J is offered A and B. Or J can pass and come back to I, right? The interesting case here is if, say, agent I prefers B to A, right? So he doesn't want to take A at the first move because he might do better. So A, the first move is not obviously dominant, but the question is passing obviously dominant? And I claim that it is, so I don't think I have a light here, but maybe, no, all right. But passing is obviously dominant because, well, we can just check. What's the worst case from passing? Well, if J takes A, then we're going to give I B. That's better. If J takes B, we're still going to go back and offer I A again. So even in the worst case, he'll still get I, so passing is obviously dominant. Okay? And this is not a serial dictatorship. Okay. What about another example? Here's another example that gets a little bit more complicated. What if there were 100 objects? The agent prefers them in order of their index, and his first move he's offered number 2, right? And maybe, in this game, it is also obviously dominant to pass, but he may not be offered his first object for sort of hundreds of moves later. Some game paths will get it, some he won't. This is significantly more complicated, right? And I just want to point out that even kind of trying to describe this game can be pretty complicated. If I wanted to just linguistically, write out what this game, how this game works in words to somebody, it would take me lots of, if statements and contingencies to describe all the various possibilities if you pass, right? But formally, this game does turn out to be obviously strategy proof, which is going to be a implication of our first main result, which is a characterization of OSP mechanisms in these environments. We characterize them by a class of games that we call Millipede games. They're going to have this clinch or pass structure, which may kind of remind you of the centipede game, but they have more legs, so we call them Millipede games. Centipede with more legs, right? So it's going to be a finite, extensive form game of perfect information, such that actions are divided into 2 types that I've already basically introduced to you. The first is clinching actions, where your outcome is completely determined, and you never move again. The second is a passing action, which means that several outcomes are still possible for you. And a key feature of a Millipede game is that there's at most one of these at every history, right? There cannot be more than one passing action. But that's not the only thing that we need. We still have further restrictions. We have to restrict what can happen after a pass as well, right? And this is where it gets a little bit complicated in the notation, so I'm going to try and do this in words. So the basic idea is that if something that was possible for you, but not clinchable, disappears because someone else took it, then I have to return to you and offer you at least everything else that was previously clinchable to make sure you don't regret your decision to pass on one of those things, right? On the other hand, if something that was clinchable for you disappears because someone else took it, that could also happen, then I have to offer you at least everything else that was possible but not clinchable. Because one of those things could have been, because that thing could have been your second choice, and so you have to get your first choice. So that's the sort of the heuristic description. Here's the formal definition, which I'm not going to spend a whole lot of time going over. I just want to show you that we have it. The notation that I will use a little bit later in the talk is on these top 2 lines. So P will be the outcomes that are possible at H, and C will be the outcomes that are clinchable at H. Using this notation, we can define a Millipede game. The first part A is just this one passing action part that I mentioned. The second part is basically formalizing these 2 bullet points. But don't worry too much about that. You can see the paper if you're interested. But the main result then is that a mechanism is obviously strategy-proof if and only if it is equivalent to a Millipede game. Right? So there's one word here that I have to define for you, this word equivalent. It's very easy to define. It just says, if you give me some game that has an obviously dominant profile of strategies, I can give you another game that also has obviously dominant strategies that is a Millipede game and that gives the same outcome for every type profile. That's just outcome-based equivalence. That's all it is. Okay. So that's our first characterization in terms of this. You might ask now, so okay, there's some complicated notation. What does that actually mean? What kinds of games satisfy this, right? Well, here's some examples. First, as I already mentioned, are serial dictatorships. Here's where Yana is going to come back. Second will be dual dictatorships, which he talks about in a paper with Itai Ashlagi, and I have some other work on this as well. Slightly more complicated, so I'm getting more and more complicated as I go down this slide, is another paper that I has is sequential barter with lurkers, which I'll come back to in a few slides, so put a pin in that for a moment. This game before is also a Millipede game. And finally, so I'm going more complicated down the slide, this last example, while not technically a Millipede game, I put it on the slide just to illustrate the potential complexity of obvious dominance, which is chess, right? So if white has a winning strategy in chess, which I'm not a chess expert, I think folk wisdom is that's probably true, but it's as yet undecided. But if that is true, then in chess, white actually has an obviously dominant strategy, right? And yet, the strategic choices in chess seem kind of far from obvious, right? So this kind of motivates us to think of, what's going on here? Why is obvious dominance allowing these seemingly complex games? And if we go back and look at the definition, look at something that we kind of skipped over before, when we're taking these maxes and these mins, we're doing it only over S minus I, right? So this is saying I'm fixing my own strategy. I know what I'm going to do in the future, but I take the max and the min over my opponent's strategies, right? So this does allow for agents who maybe not be able to contingently reason about outcomes state by state based on their opponent's actions, but it presumes they can do so at least with regard to their own future selves. I know what I'm going to do in the future, and I know the possible outcomes conditional on what I'm going to do in the future at every single possible history, right? And the problem here is this may still require significant effort or foresight to actually find the obviously dominant strategy in the first place, right? And so to try and, so this is, you might want to call this, hyper-rationality. This is sort of an often criticized weakness of game theory. And so we're going to try and relax that a little bit and try and capture agents who may not be able to, may not have such extensive foresight to look so far into the future of a game. And this is going to introduce our general class of simplicity concepts, of which OSP will be a special case. Okay? So if you've seen this paper before or read it, this part here should be pretty new to you. So this is very new. It's in the newest draft that we just posted, so comments are certainly appreciated. So the question is, how are we going to do this? So our idea is we want to allow the agent's perception of the strategic situation to vary across the nodes at which the agent moves. Okay, so as we walk through the game, you're going to find, you only have limited foresight, basically. You can only maybe look a little bit ahead in the game, and that can vary. You can update your plan of action as you sort of walk along the game path, right? So the way we're going to formalize this is by introducing this set H sub I H star, which is going to be the set of future nodes that are going to be perceived as simple at H star. So this is going to be a parameter of our definition. It's the set of, starting at a node H star, it's the set of continuation nodes that I view as simple. It's just a set of nodes. We're just going to call them simple nodes, and we're going to vary basically this set. One example could be that this set is the set of every continuation node at which I moves. So this is going to give us back basically OSP. We'll see in a second. This essentially means that I can plan all future moves. Okay? And so for simplicity, we assume that the node you're currently standing at, H star, is simple, so it's in this set. And we're only going to consider subsets that are nodes at which I moves. So the HI on the other side is all nodes at which I moves in the game. So the set H star is going to be a subset of that. Okay, so it won't include any of your opponent's nodes. Okay. And so with that given as a parameter of our definition, now we can introduce the idea of a strategic plan. Okay? So a strategic plan, this is going to be a little bit non-standard. It is not a strategy, right? So as I try and explain to my undergrads every year, often very futilely, a strategy is a complete contingent plan of action, right? This case, this is not a complete contingent plan of action. A strategic plan only gives you directions of what to do at simple nodes. So at non-simple nodes, there's just no, it's not defined, right? So it says, this will SI of H star of H is the action that you plan to take at a simple node H in the future when you're at node H star, okay? And then we're going to say that a strategic plan is simple, so we're going to do, for nodes that are not simple, we're basically going to do the same min-max comparison. So we're going to say that at H star, your plan is simple if the worst case that you get over all game paths satisfying the restriction that you're playing your plan in the future is better than the best case from doing anything else at H star. Okay, so this is just the same, min-max approach, kind of pioneered by Sheng Wu, but just in only for simple nodes. And if it's not a simple node, then we just take the min-max over all continuation nodes. Okay. And so for every node, H star will have a strategic plan that we put them together in a strategic collection, and we're going to say a strategic collection is simple if all of its strategic plans are simple. I should highlight at this point that along the game path, agents are allowed to refine their strategic plans. So they may not be consistent, right? You may think you're going to do something today. Today you may plan to do something tomorrow. When tomorrow comes, your plan may change, right? That's kind of the point. We're trying to exactly capture that. That's the whole point of the definition. Okay. All right. So maybe some examples will help. So remember, this set H sub H star is going to be a parameter of our model, and enlarging or shrinking the set will give stronger or weaker simplicity definitions. So the smaller this set is, the fewer simple nodes, the more stringent this inequality is, and the stronger the simplicity concept. So in particular, if we go back and we get H star, Hi of H star is all future nodes, then we get back OSP. If you've seen an earlier version of this paper where we talked about strong OSP, this is the case where the only simple node is the node you're currently standing at. So nothing in the future is simple. Right? So you cannot plan any moves ahead. All you can really plan is for today. You can also look at intermediate concepts, and we're going to look at one in particular that we call one-step simplicity. One-step simplicity means that you can plan at any node that is one move ahead, so any node H where you don't move you are not called to move between H star and H. So you can plan for any next node, but nothing beyond that, right? And just to bring back to the consistency point I was making, so OSP, the strategic collections need not be consistent, but sometimes they are. So OSP strategic collections will be consistent. SOSP ones will be also, just kind of trivially. One-step simple strategic plans, though, need not be. And that brings me back to this idea brings me back to an ascending auction, okay? So ascending auctions, we know they're OSP. They won't be strong OSP, but it turns out that they do satisfy something stronger, which is that they are one-step simple, right? So I think maybe this will, if you're still confused by this definition, maybe this really simple proof will explain, help you understand the definition of what a strategic plan is. So to show ascending auctions are one-step simple, well, we just need to come up with a strategic plan that is one-step simple, right? But that's pretty easy to do, right? In an ascending auction, the price is rising, one increment at a time. Our plan says, for any H star, if the price is below your value, stay in with a plan to drop out tomorrow, right? And then when you get to tomorrow, you're going to update, right? Stay in with a plan to drop out tomorrow until you hit your value, in which case you drop out immediately. So this will be one-step simple, and so ascending clock auctions will be one-step simple. Okay. So Sheng Wu generalizes this a little bit in his paper. So he shows more generally for binary allocation settings with transfers. He shows that OSP is characterized by a class of mechanisms he calls personal clock auctions, which are a generalization of just a simple ascending auction. Using our framework, so this can actually be strengthened to OSS. Right? Because OSS implies OSP, so one direction is easy. All you really need to show is that these personal clock auctions are also OSS, which it turns out that they are. Let's go back to this environment without transfers, right? So what is this going to do to this game, right? Well, OSS will eliminate these types of complex millipede games. It'll eliminate things like chess, right? And it'll eliminate things like this. And the reason is, so just very simply, so consider this agent again who prefers objects in order 1 to 100. At the first node, so one step ahead is this node 03 there, but then after that, we just take the min of all future histories, right? So no matter what you plan to do at that next node, the worst case is worse than just taking 02 today. So this game is out, right? So it does eliminate at least some level of complex millipede games. And like I said, it'll eliminate very complicated things like chess as well. But it does allow for more things than serial dictatorships. And it allows for particular things like this. So this example is due to Yanai and Sophie Bade, which they call sequential barter with lurkers. What's going on here is there's 4 objects, x, y, z, and w. At the first node, agent I is offered all but w. If he likes w, it's going to be obviously dominant, and indeed, I claim I'll show you one step simple to actually pass. And why is that? Well, the reason is, look at any next node, right, which is the red nodes. All of his next nodes are the red nodes. At any next node, he either gets w, which is his favorite choice, or he's offered again x, y, and z, right? So the worst case, even one step ahead, is either his best thing, or he gets a free choice from what he was offered before. Right? So he should pass, and indeed it's one step simple to pass. Okay? And so these games, this class is the games that look like this. We're going to give them a name. We're going to call these games monotonic. And so we're going to say a game is monotonic if for any 2 immediate successor nodes where I moves, so he doesn't move in between h and h prime, one of 2 things holds. Either you're offered to clinch everything at h prime that you were offered earlier, so your clinchable set expands, or you were offered to clinch everything that is possible but that was not clinchable earlier, right? And then we have a result that a game is one step simple if and only if it is a monotonic millipede game, right? So this game, for example, is monotonic, right? So if you pass, you're either offered to clinch everything you were offered before at that far right node, or you're offered w. So one of these 2 things will be satisfied at every node, right? And so is this game, simple or not, right? What is this? Intuitively, what do we think about this, right? So the way I think about it is, this game it looks kind of complicated, and I agree it was very complicated for Yanai to find. Or maybe it wasn't, maybe he's really smart, but I think for most of us, I'm sure he is, he came up with it somehow. I don't know how he found it, but it's a very hard game to find. But I think once you found this game, it's arguably maybe not so hard to actually play. And not only that, once you found the game, it's actually not too hard to describe step by step to the agent what's going to happen, right? So at the first node, all you really need to say is, well, if you pass, you're either going to get W, or I'll give you everything you have today. This is different than this really long 100-move millipede I showed you before, where there's going to be lots of contingencies, and it's going to be very hard to describe the game. So I think, in some sense, these games maybe are actually capturing what it means to be simple to play. Okay? All right. The last few things. So going back to this case where the simple nodes are only H star, agents can plan no moves ahead. We get an even simpler class of mechanisms. And so I have 2 results here. They're basically the same results. One's without transfers, one's with transfers, but they're pretty much the same thing, just different terminologies. Without transfers, we say a mechanism is SOSP if and only if it is equivalent to what we call a curated dictatorship, where a curated dictatorship is just like a normal dictatorship. I call you up to move one at a time, and I offer you some objects. The reason it's a curated dictatorship is that I may not offer you everything, so the game may curate what you can get. Okay. If we add transfers, these just become personalized or posted price mechanisms. Okay. Same thing, we just add transfers. And I'm running out of time, so I put in this slide because I'm at EC and I wanted to talk about computer science stuff, but I'll have to skip it. Sorry. So, because I wanted to at least tell you our results on how we characterize this random priority mechanism. Okay, so in object allocation, we know that deterministic serial dictatorships are strongly obviously strategy-proof and Pareto efficient. That's very easy. The problem is they're not fair, right? Because the first person in the deterministic ordering always gets the same thing, or his favorite thing. And the standard solution here is that we symmetrize this by choosing the ordering of the dictators at random, right? And that gives us random priority, okay? But we can do that with any game, okay? So not only this game, we can do this with any game. We can symmetrize any game in the same way by just having nature take a base game, have nature choose some permutation randomly. The agents then play that game with that permutation, right? We're going to denote this random mechanism by gamma star, okay? For instance, if gamma is a deterministic serial dictatorship, then gamma star is going to be random priority. Our first characterization of random priority is, so there's all kinds of complicated OSP and deficient games, right? These sequential barbed lurkers, there's all kinds of stuff that can happen. But if you symmetrize any of these games in this way to make them fair, you will end up with random priority, right? So I would like to talk about the proof, but again, I'm sort of running out of time because Ramesh is already standing and staring at me. So let me just give one more slide, and then I'll be done, which is we want to give also a second characterization that we can provide that weakens the fairness requirement if we use SOSP. So a very natural fairness requirement is to say that a game satisfies equal treatment of equals if any two types receive the same distribution over outcomes, right? It's easy to show, again, that RP is SOSP, efficient, and satisfies ETE. This is very well known. Our result goes the other way and shows that it is the only mechanism that satisfies these properties. So if you care about these things like efficiency, fairness, and simplicity, at least as we've defined them, what we're saying is there's basically only one choice. And so this is an explanation for why we see random priority used so much. These are very nice properties. If that's what you care about, it's basically all you can do. And one final remark is we actually have a third characterization as of yesterday that we can actually characterize this using only OSP and ETE if we weaken the equivalence concept to individual outcome equivalence. So equivalence basically of marginal distributions rather than of the whole distribution over allocations. Okay, my conclusion slide. I'll skip it. I'll just leave it up here, and we can take questions.
Time for one or two questions. Were you guys all out drinking last night? Oh, there we go. Vince, go ahead.
Oh, yeah,
I
don't.
Let me just repeat the question really quickly. So he was asking, let's say, if I think about one-step obvious things, but you know that I think about two-step obvious things, sort of what impact does this have on?
Yeah, that's something I had not ever thought about. It's an interesting question, but I can't say I have anything insightful to say about that at the moment. Sorry, that's an interesting idea.
I think I saw one other hand up over here. Jason?
So, what happens if you care about efficiency before the randomization? This is ex post efficiency.
This is ex post efficiency, yes.
1 second again. What happens if you care about efficiency before the randomization? Because Peter's results are ex post efficient.
Yes, our results are all ex post efficient. And so there certainly are, results that have looked at things like this with ex ante efficiency and things like even in between concepts like ordinal efficiency. But yeah, I'm not, again, I don't know. Sorry, I have nothing, I can't remember right now what those results say. But there are people who have looked at these things, so, yeah.
Anyone else? Okay, all right, why don't we thank both Yanai and congratulate them, and Peter.
All right.